Yo, what's good, guys? Today we're going to be going over two integrals from the Cornell, basically extreme integral packet. Um, so yeah, let's get started. So, knowing how this problem works and basically seeing a walkthrough, not a walkthrough, but like it being done before. I know that this has to be done by polynomial line division, and it can't be done by any other methods really. At least not easily. So, you know, there's no way of you knowing how to do or that's what you're gonna need to do. At least not instantly. So, um, just acknowledge that, this isn't, if you didn't instantly see that, it's not your fault. There's practically no one in this planet who could have done that. Not on this planet, but there's practically no one who would have tried that at least first and been able to see this problem to say, oh yeah, polynomial line division. So to do polynomial line division, I'm not going to do it like completely this entire time for this entire problem because it will take forever. But I'm just going to do the first like two and then just write the answer. So x squared, or x to the, so starting out, you want to do x to the fourth divided by x squared. You want to take the highest degrees and divide them by each other, and this is equal to x squared. So you have x squared plus, well, integral, x squared plus, whatever's going to come next. So what you're going to want to do now is times x squared by x squared plus 1 by your denominator. You want to times what your division is by your denominator. This equals x to the fourth plus x squared. And then you're going to subtract it from your numerator, like all of it. So plus 2x cubed plus 3x squared plus 2x plus 1 minus x to the fourth plus, this is supposed to be x squared. So these obviously cancel. And then since this is 1 and it's being subtracted, this becomes 2. So your thing, what essentially you're doing now, what this became was x squared plus 2x cubed plus 2x squared plus 2x plus 1 all over x squared plus 1. You basically just took out an x squared and then you had to change what this looks like. So then you're going to want to do the exact same thing. Divide your degrees, your highest degrees. So 2x cubed over x squared equals 2x. So then you're going to want to do 2x times x squared plus 1, which is just 2x cubed plus 2x. So then you're going to want to subtract them. So 2x cubed plus 2x squared plus 2x plus 1 minus 2x cubed plus 2x. So this, obviously the 2x cubes cancel out, and then this and this are going to cancel out. So now your integral, since you took out a 2x right here, your integral is now plus 2x. And then what you did is you made it so it's x squared plus 2x plus, let's see, 2x squared plus 1 over x squared plus 1. Okay, so do the same thing. Okay, 2x squared over x squared is equal to 2. So once again, just go back up here, just write 2 in. And then you're going to want to do 2 times x squared plus 1. I'm just going to write the entire thing now. From 2x squared plus 1. And you're going to want to minus this. These are going to cancel, and then it's going to be 1 minus 2, which is equal to negative 1. So now you did x squared plus 2x plus 2 minus 1 over x squared plus 1. And this is your entire integral. Because 1 over x squared, there's no simplification there. There's nothing that the x doesn't, get out. It doesn't equal anything really. So like there's no way that you can take out and make it like equal to like a number, it's always going to have an x in there at that point. So minus 1 over x squared plus 1 dx. Now, these first three are just basic integrals. Arguably, this last one is as well, but regardless. Plus x squared plus 2x. Now this last one, I'll just write negative because I know it is. But this last one, it's a trig identity. It's a an arc sign, or a inverse trig identity. I mean, it's supposed to be arctan. The way I remember it is it's like tangent and sine are always positive, and then cosine's just negative, and then sine and cosine have square roots on the bottom. That's basically it. If it has a negative in there and there's a square root on the bottom, it's cosine, and then you add it. But if it's positive, then it's sine. So I mean, negative in here is essentially what I'm saying. So yeah. So this and then plus c. This is your answer. Okay. Moving on to the next one. The next one is doing it in a different color. Oh, that's not the color I want. Get a nice integral sign. There you go. E to the x sine x dx. Okay, so looking at this, you should be able to tell that u substitution won't work because what are you going to be substituting u for? Substitute it for sine x. There's no cosine, you can't make one. Substitute it for e to the x. Well, you still have a sine x left over. Substitute it for x, and it makes no sense. So u substitution doesn't work. Polynomial long division or partial fractal decomposition doesn't work because it's not a fraction. It's not rational. It's not a rational equation. So the only thing that you have left, outside of doing some like heebie-jeebie stuff, is integration by parts. Which, knowing e to the x and trig functions is almost always what you'll end up doing, especially when they're multiplied. So dv equals e to the x, v equals e to the x as well. Just u equals sine x, and then du equals cosine x. So with this, you can, if you know the formula, you should know the formula. It's uv minus integral of v du. So uv minus integral of v du dx. So put my thing up there. So looking at this again, now we're onto this. It's kind of the same idea as this up here. You know, cosine, and you have a trig function and a logarithmic function, or an exponential, whatever you call it. So you're gonna want to do integration by parts again. There should be a dx here, just be right. So I'm gonna do this in a different color. But you're gonna want to do another thing of integration by parts. And when you do another one, you usually want to keep your dv and your thing and all this basically the same. You just want to move it down, and you know, if you have a trig function here, you just want to write your trig function here. And same thing up here. You want to keep the types of expressions they are the same. So u equals cosine x, and then du equals negative sine x. Okay, so e to the x sine x minus, and then all in the thing, because you're going to do another, all in parentheses, because you're going to do another thing, and this is subtracting all of it. So e to the x cosine x minus integral of v du e to the x negative e to the x sine x dx. Should also be a dx here. So looking at this, you may say, oh, we'll move this out in front first. You may say like, oh, this is like the same integral as up here, and you'd be right. And especially since this is equal to this, you may say, well, is there some sort of canceling I can do? And that would be smart, because indeed there is. You can basically treat integral functions, or not integral functions, but integral expressions as you know, like a value or whatever, because these are going to equal the same thing. These two things are going to equal the same thing, no matter what value of x. So what you're going to want to do is basically, if you can just like move this over and just see, oh, this is just 2 times this, then that's great. But you know, some people might want to like think of this like as z, and like think of these as a exponent, or a not an exponent, as a variable all in their self. So it's easier to just, and it's more clear to do the algebra. Sine x minus e to the x cosine x minus z equals z. And then you might say, oh, okay, well, I'll just move this to the other side. It's just like algebra 1. So e to the x sine x minus e to the x cosine x equals 2z. And you may say, okay, well, I need to figure out what z equals, because z is just one of these integrals, and that's what we're trying to find. We're not trying to find the basically double of it. We're not trying to find what both these integrals are when added. We're just trying to find what one of them is. So the way you want to do that is clearly by just using algebra. You just want, I'm going to move this 2 to the other side, obviously. All this divided by 2 equals z. And then you're going to want to fill in z, which is, you know, integral of e to the x sine x. So this is your dx. This is your answer, essentially. You can even go one step further and fully simplify this and say e to the x over 2 times sine x minus cosine x equals e to the x sine x dx. You know, I took out an e to the x from both these, and then I just, because it's being multiplied and it's on top, I can just put this over 2 and then multiply it. So this is, and then plus c. This is your answer, essentially. You know, you don't have to write the, you don't have to write this. This could just go. So yeah, that's basically how you do it. I really like this last problem especially, just because I find that it really like shows something that like not a lot of people really like think of. Like a lot of people understand that, oh, like when they get this far in a problem and they can do this, they're like, oh, you know, I know how to do this, just algebra. But it's just like it's putting that thought in your head before you even start the problem, which I find really interesting. So I feel like these sorts of problems like really enhance your ability to do like like integrals like this, more complex integrals, where you know you're going to be moving things around a lot, because you're thinking about it before you even do the problem. And so yeah. So I really hope you enjoyed this, and I hope that you are thinking of something new that you can even do with integrals. So thanks.